Good morning, everyone. The plan for today is the main thing is to look at number 3, a common source as an amplifier. We looked at this in the face-to-face lecture on Wednesday. So today we'll complete that. For us to be able to do that, we need to know what current mirrors are. So we'll do that first. And once we've done that, we should be able to introduce the differential amplifier, which is key to VLSI design. I hope you can hear me loud and clear, and that you can see the stuff here. Formally, we should be starting the labs today, but I don't yet have confirmation that the lab is ready. So I'll write to the class later on after this lecture. I have another lecture after, but I'll confirm and email the class if the lab is available for you to start using for your lab. If in case there are any questions from the last lecture, you can do the usual. You could type it in the chat or unmute your mic and ask. Otherwise, we get started with today's lecture. So we are familiar with this. For a PMOS, the characteristics look like that. VGS1, VGS2, VGS3. And the model for this, we already looked at it. So if that's VGS, that's drain, gate, source. That's IDS. And in this region, the model looks like that. So in the active region of the transistor, the current is constant. It doesn't depend on VDS. So if so the question is, what is the internal resistance of IDS? So current source, we should know from electronics that current sources have a high internal resistance. So if we are somewhere, if our operating point is there, what would be the what would be the resistance of the current source? The current source gives a constant current, but the equivalent resistance, how much is that? We can get that by changing VDS. So if we increase VDS by a value delta VDS, the question is, how much does the current change? So we know from the V characteristic that so the internal resistance, which we can call RDS, the resistance between the source and the drain, will be equal to the voltage that we put between the two main terminals, the D and the S, and the change in current. The change in current is 0. So this number is a big number. So the internal, so the internal resistance is quite high. It's ideally infinity. Usually the IV characteristics will have a small positive slope. So the internal resistance will be in kilo ohm or mega ohm, minimum kilo ohm, otherwise mega ohm or higher. So the internal resistance of a channel length modulation, I would say, so we need to worry about that when the speed of the devices, when the devices become very small, then we would worry about channel length modulation. Whatever that means, yeah, so for most people that will not be clear. But for this course, the amplifiers we're looking at, that is not important. We assume that doesn't affect the device significantly. So the small signal, so the large signal, we write it like that. We draw it like that. The small signal, we can, as we saw last time, the current source, small signal current, we can write it as transconductance times VGS. And between the drain and the source, we can have a resistance RDS, and this resistance is a large resistance. That's right. The resistance is high. It's unlimited. If you want to put it that way, unlimited is probably not the right word, but it's you know that symbol. The English word for that is a very large number or infinity. It's a high resistance. And the reason I mentioned that is remember our current our common source amplifier. So I'll jump a little bit to point number 3 before we go back to current mirrors. We saw on Wednesday that V out over V in, or the gain of this amplifier, is given by minus GM times RD. And therefore, if we want the gain to be very high, we make RD to be as high as possible. And what we do is we replace this resistance with a current source. So if we have a transistor which is in the active region, then if we have a transistor that's in the active region and put it here, its resistance will be very high. So the gain of our amplifier will also be very high. And the reason to use the transistor is even though the resistance of the transistor is very high, it still allows a current. So the current that goes through this is the same as the current that goes through this transistor would be the same as the current that goes through this transistor here that offers an equivalent high resistance. So if we do that, the circuit would look like this. So just one thing. So this is VG. As the gate to source voltage increases, the current through the device also increases. The point at which this voltage, we call it the knee voltage, as I've already mentioned. So the point at which the current saturates or flattens out. So for low drain to source voltages, the current increases linearly, but after some point, it flattens out. This point at which it flattens out So for this curve here, VDS is roughly equal to VGS. And this is explained in the earlier pages in the handout if you read through, that when you increase your drain to source voltage, the point at which the drain to source voltage equals the gate to source voltage, then the current flattens out. So if our gate to source voltage is higher, we need a higher VDS before it actually flattens out. So one way to ensure this condition, in the textbooks, it might also be referred to as the Pinch-off condition, but a simplistic way to look at it, or looking at it, a broad view of looking at it, is when VDS increases. When it's less than VGS, the current will be rising, but as soon as it's greater than the gate to source voltage, the current flattens out. So for us to achieve this condition, we draw the VDS approximately equal to VGS. If I'm using an NMOS transistor, I can achieve that condition in a fairly easy way. So that's my source, that's my drain, and that's my gate. Actually, if I connect D to S, this means that VDS is equal to VGS. We say the transistor is said to be diode connected. The transistor now looks like a two-terminal device, or it's actually a two-terminal device because this terminal and that terminal, we've shorted the two of them. And so the voltage across the drain and source is the same as the voltage across the gate and the source. Often that expression is used, that the transistor is diode connected. That simply means that instead of having 3 terminals, we now have 2 terminals. So because of this connection, this transistor is either off, so IDS is equal to 0, or it's on, IDS in saturation region. So depending on when we connect the device in the circuit in this connection, it will not pass through the region where the current increases linearly with increasing VDS, because VDS is tied to VGS. And so if you don't have enough voltage across the device will be off, otherwise it will be on. And between the drain and the source, because it's in saturation, the equivalent resistance will be very high. So that means that our common source amplifier, which looks like that, well, that's our D. I can call this as Q1, and that's VDD. This one, we can, if we use this device as our load resistor, then we can we can load the transistor like this. So I'll have VDD, and I'll have my top transistor, and this one I can connect to that, and this is my amplifying transistor. That's my V in, and this is my V out. So instead of having a resistor at this point, we can have a transistor at this point, but the drain and the source, they're connected together, and with that connection, this transistor is direct connected, and so if VDD snap that a current flows through here, this transistor presents a high resistance to the to the amplifying transistor. So if I call this transistor Q2, we call it an active load. So it's a load. If we use a resistor, this one, we would call it a passive load. So this a load that dissipates, here we'll have I squared R loss. But in this active load, we actually don't have it has an equivalent high resistance, but we don't have dissipation of power in this resistor. And so we call that an active load. Actually, as we'll see shortly, we normally would because the current flowing through here is the bias current IDS. For good control of IDS, we need what's called current sources, current mirrors. So at the moment, this circuit has theoretically it does what we say it does, but we cannot set IDS. IDS cannot be set. We cannot set IDS to a value that we really want. So it's not okay for teaching, but it's not a practical circuit. For us to be able to set the bias current flowing through this to a value which we want, we need to understand what current mirrors are, and we'll see how they feed into that. So it's a current mirror. In a current mirror, so you have a circuit, if I make it as a black box, you have, I think I make it as two black boxes. So if I have a reference current flowing through that, then I have I out to be equal to I reference. Yeah, IDS cannot be set precisely. So the circuit which I just had, we cannot set IDS to the biasing current to the value which we want. Yeah. So yeah, but through current mirrors we can be able to do so. And yeah, let's just discuss what current mirrors. Yeah, what's a current mirror? That's not quite a good illustration, but you have a reference current that goes into the circuit. Probably should be one box, and that you have an output current that is identical to the input current. So it's as if you have a mirror. So if I have a current flowing into this box, an identical current flows into the other box. We have the circuitry in between, and because the two currents are identical, we can say that we have a mirror effect. So the current here is a mirror current to the reference current. How we do that, we use the transistor characteristics, and I'll use the NMOS device to illustrate this. So if I have an NMOS device, And this one is IDS. I can call it IDS ref. So the reference current IDS is precisely set by VGS. So VGS sets IDS, which we can call this as our reference current. So given any transistor, in this particular case, a PMOS transistor, if I choose the value of VGS, I fix the value of IREF. So if I want this current to be copied in another circuit, so that if this is IREF, it's also flows in a different circuit. The way to do that is I have a second transistor. So I have my, I'll redraw this. I just redraw it the other way around. My second transistor, I can have it there. So this is Q1, Q2, and that's my Q1. We know that, so for Q1, we know the important voltage to set IREF. The important voltage to set that is VGS. So if I want the same current to flow through another transistor, the other circuit could be another transistor, is I could connect the other transistor to the first transistor such that the get to source voltage of the second transistor is identical to the get to source voltage of the first transistor. And if I just do it like that, then this transistor, it will be in the linear region and in any of the regions. But we'd like this transistor to be in the active region all the time. And so we can connect the gate of the first transistor to the drain of the second transistor. That means that the current flowing through this will always be in the saturation region, and I out will be equal to IREF. And the reason for that, because the get to source voltage VGS1 is equal to VGS2. VGS sets the current through transistor Q1, and VGS2 sets the current through transistor Q2. So of course, this is only true if transistor Q2 is physically identical to transistor Q1. So Q2 and Q1 must be physically identical. So for them to be physically identical, we make the transistors on the same chip. So make them on same chip. Maureen, just 1 second. So we make them on the same chip next to each other. If you make them on the same chip and they're far from each other, there will be local variations. The transistors would be a bit different. And so that will not be good enough. So when we make them on the same chip, and we call this monolithic technology, or we make both devices from the same material, from the same base material. Yeah, how do we make sure that the device is in saturation? Is this connection? So the gate, if you look at transistor Q1, which is the master transistor, VDS1 is equal to VGS1. So this transistor is diode connected, and as we've just seen, if the transistor is diode connected, any current flowing through this transistor will be a saturation current. So it will not go through the linear region, So it will, this transistor will always act as this means Q1 always acts as a current source. So we'd like Q1 to act as a current source. And the reason for us to want Q1 to act as a current source is so we can use it as the load of our common source amplifier, because if it's a current source, its resistance is very high. So we don't want this transistor Q1 to go through the linear region where the current is increasing with VDS. So it's either, if the circuit is working, this transistor should be in saturation region. If it is, transistor Q2, because transistor Q2 is made identical to transistor Q1, the difference is that we don't have gate to drain connection for transistor Q2, but because they're identical, the control voltage is the same. Q2, so Q2 must be active. Q2 must be active because Q2 is controlled by gate to source voltage VGS2, but the gate to source voltage of transistor Q2 is the same as the gate to source voltage of transistor Q1, and we know that for this type of transistor, the gate to source voltage determines the current that flows between the drain and the source. So Q1, make sure that the current flowing through this transistor is in the saturation region, and Q2 will copy whatever current flows through Q1 will be the same as the current that is flowing through Q2. So there was one question from the chat. If you give me a second, so for transistor Q2, how do we ensure that it's in saturation? You ensure that transistor Q2 is because Q1 is identical to Q2. And no, it doesn't depend on the load. So that's why it's called a current mirror. Yeah, of course, it depends on the load. It will either be in saturation or there'll be no current flowing. Because Q1 is diode connected, so this transistor Q1 will be in either it's either off, so no current is flowing. But if current is flowing, this transistor will be in saturation region because of this connection between that makes VDS1 to be equal to VGS1. Well, transistor Q2, it's manufactured to be identical to transistor Q1. It has the same control voltage. Because we have the same control voltage, so if this is in saturation, this will be in saturation. So we call this current mirror because I out copies whatever current. So how can we vary the reference current? One of the reasons for going to this circuit is that we can vary the reference current. So if I just redraw the circuit, I'll show you how we can vary the reference current. So this is Q1, this is Q2. Ref. VDD, R load. So the current that flows through there is RF. IDS here is equal to IREF. Because this, if we vary the value of IREF, we'll vary the current that can go through this path. So we can vary the current through the reference current with this reference resistor. But because this transistor is diode connected, This transistor, if there's a current, this transistor will always be in saturation region. But Q2 is identical to Q1, and we've connected them such that VGS for both of them is the same. So the current flowing through Q2 is equal to IREF. Theoretically, for all practical purposes, whatever the value of the load resistance, it doesn't matter. The current that will flow here will always be equal to IREF. If the load is too high that that is not possible, then the transistor Q1 will switch off, so no current will go through there and no current will go through there. So it's either off or it's no, the resistance of the current source is always high. So we know that the current source has a high resistance, and we'll see why it's useful in the amplifier circuit. We'll see how to use that high resistance. We've looked at it briefly, but we use current mirrors in the amplifier to get that high resistance issue. So if you just bear with me, I'll come back to your question in a few minutes. And the question from Gennad, if VGS was too big, would it make the transistor operate in the linear region? No, VGS cannot. If we connect, if we connect this point, if we connect the gate to the drain, so VGS1, VGS of transistor Q1 is always equal to VDS. So VGS will never be bigger than the drain to source voltage because of this connection, because the two are shorted. And that ensures that this transistor is always in the saturation region. So it never passes through the linear region. If this is in the saturation region, then transistor Q2, because it's physically identical to Q1, it has the same control voltage. It also necessarily has to be in the saturation region. If there's no load, if there is, the load, it might, when you go to the lab, try this circuit out, by the way. Yeah, so with a bit of luck, you might start accessing your lab today, the lab exercise. So you can try to simulate this in the lab. So the load, if that's a short circuit, it works. If it's an open circuit, the whole of this breaks down. But any other load resistance, the current IREF will always be the same as the reference current. It doesn't matter the value of the load we put there. And try that in the simulation. The theoretical explanation might not be very clear, but try that in the simulations. If D and G is connected, can also be equal to IREF. So you're saying that if this is not connected, so what one of you is saying is that if the drain and if this connection is not there, then IDS is equal to RF. Yeah, you are right. So without D and G connection in Q1, I out will always be equal to IREF, but not necessarily in saturation region. So the caveat to that, without this connection, even though we have the current mirror effect, but this transistor Q2 is not necessarily a current source because it could be in the linear region. I can tell you that we want to use this transistor Q2 as the load in as RD in our common source amplifier. So we'd like this to be in the saturation region. And for that reason, the connection D and G is important. If that was not there, it would be a current mirror, but this would not be a current source, not necessarily a current source. So normally we have it in that configuration so that this is the current source, which means that the internal resistance is high. So for PMOS devices, that is your current mirror. And try this out when you start getting into the lab, simulate it. So that was an NMOS current mirror. And we can look at a PMOS current mirror. It turns out that the more useful current mirror that we'd like to use, we actually use both NMOS and PMOS. So let's look at how a PMOS current mirror would look like. It will also use 2 transistors. So because it's PMOS, the polarity is inverted. And I would draw it like that. And the second transistor is here. And this one, this transistor Q1, transistor Q2, and this one, reference resistor, IREF, and here is I out. And here I out is also equal to IREF. Q2 is current source. So it's exactly the same like a PMOS device, only because like an NMOS current mirror, but because these are PMOS devices, the source is connected to the highest point. So we flip it upside down. My drain and gate are connected for the first transistor. The control voltages are negative for the gate. So the gate potential is lower than VDD. So gate to source voltage is a negative voltage, which sets the current of Q1, and the current, because VGS for Q2 is the same, whatever current flows through Q1 is the same as the current that flows through Q2. So I think we had many useful questions for the NMOS device. For the NMOS current mirror, for PMOS current mirror. Any questions about this? So this RF sets IREF. So this is a transistor. It has because it's a PMOS transistor, it can have a low current flowing through or a large current. So depending on where we want to work, either there or there, by choosing this resistance RF, we can set the current that goes through transistor Q1. And no, we don't use, this is not an amplifier. This is a current mirror. This is just a, well, let's look at how a CMOS amplifier, common source MOS IC amplifier. So I'll answer your question by just doing the next bit. So our common source amplifier, we said it looks like that. RD, and we want RD to be as high as possible. So how to do that is to replace RD with a current source. And the current source that we can replace it with is actually to take this Q2 and place it here. And Q1, this Q1, we can use it. You can use it to set the current that flows through this branch. So we have control. So we can set the bias point using this reference resistor as it were. So this circuit, if we were to make it on PCB, for those who did EEE, you probably did such a circuit on breadboard, where you buy this transistor from one company, you buy a resistor from another company, you wire them up on PCB or breadboard, and you check whether you have amplification. In IC, you don't do that. We use an active load instead of the resistor. So an active load that we use would be a PMOS current mirror. So that would look like that. So Q2 replaces RG, that's Q1. And I'll call this Q3. So V in, V out, and that's my Q3. So in hybrid PCB or breadboard, that's how you do that amplifier. If you do it as an IC, we can make RD very high. So on breadboard, if you make RD very high, you'll need to increase your VDD. Otherwise, it won't support the current. If we do it like this, we can put here a resistor that sets the current, RF. So IREF will set I bias. I bias is equal to IREF. So the bias current, we choose it such that transistor Q3 is in the active region. In terms of the AC signal, for AC, it only says between that point and that point. And between those 2 points, the resistance is quite high. So V out over V in, which is equal to minus GM3, the conductance of transistor 3, times the resistance between those 2 points, I can say RDS2. And we know that RDS2 is a high number. So by replacing this resistor value with this current mirror, we can increase the gain of this common source amplifier significantly, because RDS2 is a large resistance or a large equivalent resistance. So here we say our transistor is loaded with an active load. Yeah, so V in is an AC voltage, it's a small signal voltage. V out is an AC voltage. The biases are DC voltages. So this circuit, as I've drawn it, is a complete circuit, but we can look at it just in terms of the AC signal. If we look at it in terms of the AC signal doesn't see any of this. The AC signal comes in here, it comes out here. It sees the load Q2, which is a transistor, which is a current source. So the equivalent load that it sees, the current that passes through here is the bias current for this, which is DC. But for a ref, it sees a high resistance here, and therefore V out is given by that expression, and we have a high gain amplifier. The chip, when we lay out this uses a small area compared to that, because to realize a resistor takes a bigger area. You have I squared losses in this. Here you don't quite have that. And if for this to achieve similar gain to this, you would need to increase RD to a high value. If you increase RD, you should be able to see from KVL that if you increase just this as a resistor, then you must increase VDD. Here, even though we have a high resistance, because this is an active load, or this is a current source, we don't need to increase VDD. So there are many reasons as to why this is, even though it looks a more complex circuit, it's a better circuit to do our amplification. Because this is a current mirror, so someone starts me, why is I bias equal to Iref? I bias is equal to Iref because this is a current mirror. So the get to source voltage of Q1 is identical to the get to source voltage of Q2. And therefore the current flowing through Q1 is the same as the current flowing through Q2. That connection ensures that both transistors are in active region. This circuit is what I've used. It's exactly the same that I've used to replace RG, where Q2 is in the position of RG and Q1 is our control transistor. So we set the current through Q2 by setting the current through Q1. Q2 is connected as the load of transistor Q3. So in IC, we do that. On breadboard, we do this. So in IC, we don't do our amplifier like that, but we do it this way. So one little question to the class is, so for here, I could only use a PMOS current load for the common source amplifier. I couldn't use an NMOS current mirror to replace this RG. And could you try and find that out? If you have issues, we can discuss that on Wednesday before we carry on. But this particular load resistor, I could only replace it with a PMOS current mirror and not an NMOS current mirror. If you try to put an NMOS current mirror, which is this one here that we looked at first, it will not work. And you should be able to see why only a PMOS current mirror can load this common source amplifier if the amplifier is driven with an NMOS resistor. So we have 5 minutes. I'll introduce, so we've done, so just to recap, current source, the internal resistance is very high. And we can generate a current source with a current mirror, where one of the devices is diode connected. And it's diode connected because we want to generate a current source, not only a mirror of the current, but the current which we have creates a current source. And the common source amplifiers and IC, we've looked at that. Instead of using a resistor as the load, we use, so if the common source amplifier uses an NMOS amplifying device, we use a PMOS current load to do that. So in the next 2 minutes, I introduce a current amplifier and we call it a day. So differential amplifier, I'll just give the circuit and we'll pick it up from there next week. So differential amplifier is a little bit like two common source amplifiers. So I have what looks like a common source amplifier there. Oh, that's poor drawing. I have another one that looks like a common source amplifier there. Q1, Q2. I should have. This is called a differential amplifier. I'll just tell you why it's important and you can think about it and probably read about it before the next lecture. So the next lecture, we'll look at this in detail and look at the IC form of this, and we'll look at the op-amp. So if I'll call this V in 1, V in 2. As you can see, this looks like a common source amplifier. This looks like a common source amplifier. These two resistors, we'll replace them with current mirrors so that we can implement that as an IC. So if V in 1 is equal to V in 2, the output of a common source amplifier will be there, and that will be there. For the differential amplifier, we get V out there. So if V in 1 is equal to V out 2 is equal. This differential amplifier is an important amplifier for this reason. that if the two inputs are identical, the output is 0. That's quite important. If the two inputs are different, then we have an output, and that's where the name differential comes from. That if the two inputs are different, then we have an output. And the reason for this is that in high precision circuits, if you have noise coupled onto the two inputs, the coupled noise signal would normally be identical. And we don't want to amplify a noise signal. So any noise signals that couple to the two inputs, they don't appear the output, which is pretty cool. But the signals which we want to amplify, normally we can make this a reference terminal, and we put the signal that we want to amplify here. So the signal which we want to amplify is a differential signal, as it were, and it gives us an output. So I think that's enough introduction to differential amplifier. It's plenty. You can read ahead of this. It can be slightly abstract concept, but if you consider that as a common source amplifier, it's easy to look through this, and we'll discuss this face to face on Wednesday. So have a good week and see you on Wednesday. And I'll email the class about availability of the lab. It should be available from today. So RD1, RD2, yes, yeah, RD1 is the same as RD2. Marwan, digital electronics starts next week. So this week is analog electronics for year 1, and yeah, that's a personal question, not for the rest of the class. But some of you are helping with the undergrad labs. So my first year labs, they start next week. But the VLSI labs should start this week, and I'll email the class if the lab is available. As of late last week, it wasn't yet available. Okay, see you guys. Cheerio.